Haven't had enough stoichiometry yet? Well, we're going to apply it to camels. Here's a little bit of background though about camels, in case you were made unaware about how camels' humps actually work. So camels store a fat called tristearine, that's C57, there's 57 carbons in that fat, H 110, and O 6 in their hump. So their hump is literally made out of this tristearine fat. This fat is used as a source of energy, but also as a source of water. When the fat reacts with the oxygen that the camel is breathing, the reaction literally produces water and carbon dioxide gas that they breathe out. So basically, when a camel breathes, it's literally causing a chemical reaction for water to evaporate from its lungs as the fat is metabolized. Awesome? So first things first. Let's write the balanced chemical equation for this reaction of a camel hump. We're gonna take our tristearine fat, that's our C57, our H110, our O6 plus reacting with oxygen, that's O2, to form or to produce carbon dioxide, CO2, and water, H2O. Now, of course, we need to balance this chemical reaction before we can do any kind of math with it. This is probably the weirdest and largest chemical reaction balancing you'll ever see in your life. Notice that there are 57 carbons in this reaction, so that kind of ups the ante in terms of what coefficients we're using. We're not going to be starting with 2s and 3s if you catch my drift here. We're going to have probably some triple-digit coefficients in order to balance this chemical equation. So hang tight, let's do this. Let's compare our product side to our reactant side. On the product side, I currently have 1 carbon, whereas on the reactant side, I have 57. Oxygens, I have 6 plus 2 on the reactant side for 8, and on the product side, I have 2 plus 1 to give me 3. How about those H's? On the product side, I've got 2, whereas on the reactant side, I've got 110. Let's try and tackle those carbons first. I have 57 on one side and 1 on the other, so that should be a pretty easy coefficient multiplier. Let's just put 57 in front of CO2, so that I'll have 57 carbons. But now, of course, that also distributes to the O, so 57 times 2 gives me 114 plus the one from the water. So that's technically 115 oxygens now. Hopefully you're recognizing that just as before, whenever we had a type of combustion reaction with CO2 and water as our products, and the oxygens were an odd number or an even number, those are the more tricky ones to balance, because we're always going to end up with even multipliers here, but then there's always that odd extra 1 from the water that comes about. So this is going to be extra tricky with these bigger numbers on top of it. First, let's check and see if 8 even goes into 115. If you divide 115 by 8, you get 14.375. So no, it doesn't go in evenly. That's a problem. We need them to be the same ratio value of a whole number. So let's try and figure out how we can change our oxygen value to do so. Now the next thing is that I could start by putting a 2 here so that I can make it even. I can have the 57 times 2 from here to give me 114, and then I could technically have 2 here so that would give me 116, and that would be an even number. But does 8 go into 116? No, it doesn't. That's still 14.25 if you divide the two. So that's a problem. We're still gonna have a huge number here, and just making this even in this case doesn't fix our problem. So let's try moving on to the hydrogens to try and balance those, because those are both even to start. 2 does go into 110, and let's try and manipulate that instead of the oxygen. 110 divided by 2 gives me 55. Now I did that division because I know 55 times 2 is going to give me the 110 that I need from the reactant side. So now I have 110, but that also changes my oxygen value now. So instead of 115, I now have 57 times 2, which was 114, plus 55. That gives me a new value of 169. Are we still fortunate enough yet for 8 to go into 169? If we divide those two, I still get 21.125. Not a whole number. So still not right. We're still not quite there. So let's go crazy and try and plug in a huge number instead of 2 in front of our O2 just to see what happens. Let's try plugging in like 20. So 20 times 2 would give me 40, plus 6 from this oxygen would give me 46. So that's still not enough. Let's up the ante even more. Let's try plugging in 50. If we have 50 O2s, 50 times 2 gives me 100, plus 6. That would give me 106. That's still not enough. Let's try plugging in 80. If we plug in 80 here, 80 times 2 gives me 160, plus 6 gives me 166. Well, now we're finally closer. We're in the ballpark, but still not quite there. Let's try 82. 82 times 2 plus 6 gives me 170. Well, we just missed the mark by 1. That sucks. All that work and we're still no closer. Now, we could continue doing this, and you would see that I'm just going to keep trying to plug and chug until all the values equal out. It's a long and puzzling process, but it's what you do in order to figure out when and how the atoms are all going to balance on the product side to the reactant side. Let me give you a hint here. Don't be afraid to manipulate the coefficient in front of our really big chemical. It's okay. Sometimes by doing so, it'll actually make it easier for us. So in this case, we wouldn't want to put like a 50 in front of that thing, because 50 times 57 and so on and so forth are gargantuanly large numbers. But if we have something like this, we might start with a 2, like we do for most of our chemical equations. Let's try plugging in a 2 in front of our tristearine fat and see how the rest of our atoms will adjust. Now we're back to square one and just trying this method instead, trying to put the 2 in front first. When I do that, I have 57 times 2, which gives me 114 for carbon. I also have 2 times 110 for hydrogen, which gives me 220. Now I have 2 times 6 for oxygen, which is 12, plus 2, which gives me 14. Notice that now I have all even numbers, and this is the goal. We do want all even for those multipliers in order to make it easier to balance on both sides. So that kind of took out that 57 odd thorn in our side, if you will, by putting the 2 in front and making it even first. All right, so we have 114 carbons now. Let's fix the carbons on the product side. We are just going to put 114 as our coefficient in order to fix the carbons now. 114 is now balanced on both sides. But we've also multiplied that to the oxygen when we put the 114 in the coefficient. So 114 times 2 gives me 228 plus the 1 from the water. So that would be 229 for oxygen. Now let's tackle those hydrogens. We have 220 on the reactant side and 2 on the product side. So if we take 110 times 2, that should give us 220. But that also distributes to our oxygen. So how much do we have now? We have 114 times 2 plus 110 from the water. Now we actually have an even number to work with. We have 338. Well, excellent. Can we end up with 338 oxygens on the reactant side by only manipulating this space? Let's see. Let's think about this in a logical manner. If we need 338 oxygens and we have 14 on the reactant side, we know that 12 of those 14 we don't want to mess with. So we only have 2 that we can manipulate. Let's subtract out the 12 from 338. So 338 minus 12, and I'm taking that away from this one here, the tristearine fat, so I don't mess with it. That gives me 326. So I'm trying to find a number times 2 that will give me 326 so that I don't have to manipulate the tristearine fat. Do you see where I'm going with this logic? If not, please rewind a few seconds and re-listen to that again. So 326 divided by 2 hopefully gives me a whole number that I can plug in here. Let's see. In fact, when I divide those numbers, I get 163. So now if I put 163 in front of oxygen, that's like saying 163 times 2, which gives me 326, plus the 2 times 6, 12, which gives me altogether 338. Phew! That was quite the headache of a balancing chemical equation, don't you think? If you could make it this far, now we can calculate any dimensional analysis problem using the balanced chemical equation. Alright, let's jump right into this dimensional analysis grams to grams. What mass of water, so question mark grams of water, could be made from 1 kilogram of fat. That's our triasterine fat. So 1 kilogram of this. Now, we need to go from kilograms to grams. You can't just plug in kilogram and expect that to be the same unit as grams. So first things first, let's convert the 1 kilogram to grams. 1 kilo is equivalent to 10 to the third power in grams. So when I put kilo on the bottom, the k, and make that equivalent to 10 to the third grams, I can just cancel the k and be left with grams. Essentially what this is saying then is 1 times 10 to the third power will give me units of just grams with no kilo in front. Of course, 10 to the third power is 1,000, so 1 kilogram of fat is 1,000 grams of fat. Now we can figure out how much water could be made from 1,000 grams of fat. Let's draw our magical line to freedom. Oh no! Space for our answer. And we're trying to find grams of water. We are given 1,000 grams of fat, which is our triasterine. I just don't want to draw out the molecule every time, so I'm going to write fat instead. So what's the molar mass of triasterine? We have 57 carbons, each weighing 12.011, so 12.011 times 57, plus each hydrogen weighs 1.008, and there are 110 of those, and each oxygen weighs 16, and there are 6 of those. Adding that all together, we get 891.507 grams of fat per 1 mole of fat. Now we need the mole ratio from our balanced equation. We have 2 moles of fat on the bottom for every 110 moles of water. And now what's the molar mass of water? We have 2 H's, each weighing 1, and 1 oxygen weighing 16. So together that's about 18 grams per mole. We can put 18 grams of water for every 1 mole of water. Canceling out all our units, grams of fat gone, moles of water gone. We are left with grams of water. We know we did it right, so let's plug and chug into our calculator. We're going to take 1,000 times 1 times 110 times 18 and divide that by 891.507 times 2 times 1. Dividing those two values, we get 1,110.47 grams of water could be made from 1 kilogram or 1,000 grams of triasterine camel fat. All right, now we can jump to limiting and excess reactants. That's just going to be the same thing we did before, but with 2-dimensional analysis lines, and starting with a given amount from each reactant. If the camel were to inhale about 800 grams of oxygen per day and uses only about 5 grams of fat to produce water, which of the 2 reactants is the limiting reactant between these two? Let's draw our 2-dimensional analysis lines. In both cases, our goal is to figure out how much water can be produced. So grams of water will be our goal at the end of both of these lines. For the top line, let's put the 800 grams of oxygen as our given. And for the bottom line, our 5 grams of fat. Let's do this. We need the molar mass of oxygen, which is 16 times 2 from the periodic table. And that's 32 grams of O2 and 1 mole of O2. The mole ratio comes from the balanced equation. For every 163 moles of oxygens, we have 110 moles of water. And the molar mass of water is 16 plus 2, which is 18 grams of water per 1 mole of water. Always check to make sure your units cancel. Grams of oxygen, moles of water, left with grams of H2O. Plug and chug to your calculator. When you multiply across the top, you get 1584000, and when you multiply the bottom across, you get 5216. Divide those two values and you find that you get 303.68 grams of water from the oxygen. Now what about the fat? From the previous calculation, we already found the molar mass of fat to be 891.507 grams of fat for every mole of fat. The mole ratio for fat is 2 for every 110 waters. So 2 moles of fat on the bottom and the goal mole on top, 110 moles of water. And just like any limiting reactant problem, this is going to be exactly the same. So 18 grams of water in every 1 mole of water to get us to our final units of grams of water as the goal. Always check to make sure your units cancel. Grams of fat, moles of water, left with grams of water. We did it right. Let's plug into our calculator. When I multiply 5 by 110 by 18, I get 9,900, and divided by 891.507 times 2 gives me 1783.014. Let's divide those two values. And I end up with 5.552 grams of water. Comparing these two values, we're going to pick the smaller one to be my limiting reactant, which makes sense in this case, right? The oxygen that the camel's breathing is practically infinite because outside has tons of oxygen, thanks to our wonderful plants on planet Earth. However, the fat in its hump is kind of the limiting reactant because there's not an infinite amount of fat for it to convert into water to begin with. So here it makes sense that the limiting reactant would indeed be the fat. So we can say the LR is our fat and the excess reactant, our ER, is the oxygen. And knowing this, we could make a maximum of 5.552 grams of water, theoretically. All right then, how much is in excess of oxygen after it's reacted with the fat? Moving on to our excess calculations. We need another magical line to freedom. Oh, no. And our goal now for calculating excess is going to be the grams of the excess reactant, which is oxygen. We're going to put the given of how much of the limiting reactant we started with as the first thing on our line. That happens to be 5 grams of fat. Just as before, we already calculated the molar mass of the fat, which happened to be 891.507 grams of fat for every 1 mole of fat. And using a mole ratio now between the fat and the oxygen, we see that there's 163 moles of oxygen for every 2 moles of fat. Now we just need the molar mass of oxygen, and that happens to be 16 times 2 from the periodic table, that's 16, which gives us 32 grams of oxygen for every mole of oxygen. Checking to make sure our units cancel. Grams of fat, moles of oxygen, left with grams of oxygen. Sweet, we did it right. So now we just have to plug in chart. 5 times 163 times 32 gives me 26080 divided by 891.507 times 2 times 1, which gives me 1783.014. Let's divide those two values to figure out the grams of oxygen used. When we divide those two values, we see that 14.62 grams of oxygen were actually used in this reaction. So then how much is in excess? We started with 800 grams of oxygen. So just using a simple subtraction, we find that 800, what we started with, minus 14.62, what we used, gives us 785.37 grams of oxygen left over in excess. My humps, my lovely camel lumps. Just for funsies here, assuming the average healthy camel's hump weighs about 80 pounds, or 36,000 grams, how much water could be produced if the camel had to use its entire hump? Go ahead and try and figure out this value. If you do calculate it, comment below and I'll let you know if you got it right. If you thought that camel chemistry was interesting and odd, please give this video a quacks up and subscribe to my channel for more chemistry oddities. I hope your day is just ducky. See you later, ducklings.
No ducks, no glory.